This tutorial will illustrate the approach used by SAP2000 to calculate concrete shell reinforcing intensities. These shells might be used to model slabs, domes, tanks, or numerous other structures, and we will illustrate how SAP2000 resolves shell stresses from an analysis into forces and the forces into reinforcing. Greatly simplified, the process looks like this. 1. We start with a shell section that is subjected to a membrane stress and a moment stress. 2. The moment is resolved into a moment couple and then combined with the membrane to 3. Give 2 pure membrane forces. These membrane forces are then used to determine the design forces and required reinforcing. The procedure discussed in this tutorial assumes that there are 2 layers of reinforcing. That is, there is a top layer and a bottom layer of reinforcing in 2 principal directions. SAP2000 offers concrete shell reinforcement design following the guidelines as prescribed in Eurocode 2, 1992. It assumes the section to be cracked, and the design is intended to satisfy strength requirements only. No code minimums or serviceability checks are included. Additional information on the design approach used in SAP2000 is contained in the technical note provided with the program. SAP2000's shell design determines the amount of reinforcing required on a per unit width basis needed to carry membrane and moment forces. Our example will use a 32-foot by 32-foot slab, 12 inches thick, simply supported around the perimeter. Although this is a two-way slab and SAP2000 calculates reinforcing in both directions, we will simplify our tutorial by only concerning ourselves with results in one primary direction, and in this case it will be the local 1 axis, which is the red axis. Shells typically have 8 force resultants, 3 membrane components, F11, F22, and F12, 2 flexural moment components, M11 and M22, and 1 twisting moment, M12, along with 2 transverse shear components. The thin shell is idealized as a sandwich model, comprised of 2 outer layers that contain the reinforcing and an uncracked center core. The design assumes that the outer layers carry the moments and membrane forces, and that the uncracked center core carries the transverse shear, although transverse shear is neither checked nor designed for in this shell design procedure. The design in the program resolves membrane stress and flexural stress resultants into pure membrane forces, which are then combined into reinforcement forces. In this image, the equations shown deal with the stresses in just the one direction, the primary direction we are concerned with, although in a typical slab there would be similar components in the 2 direction as well. We are only dealing with the 1 direction to make our discussion simpler. In addition to the thickness of the slab, the key piece of information to be entered by the user is the cover for the reinforcing, needed at the top and bottom locations in each direction. For instance, CT1 is the cover over the top reinforcing and is the distance from the outside of the shell to the center of the reinforcing. CB1 is similarly the cover for the bottom reinforcing. We can set the cover for our concrete shell or area object by going to the Define, Section Properties, Area Sections command and selecting our shell section. Clicking the Modify Section button, note that the thickness is set to 12 inches and then click the Modify Show Shell Design Parameters button. We select a rebar material, which for this model is A615 grade 60. And for the rebar layout options, we will select the 2 layers option. We will assume that direction 1 has the outer bars and will assign a cover of 1.5 inches to these bars. We will assign a cover of 2 inches to the inside or direction 2 bars. Now that we have entered the slab thickness and reinforcing covers, the program has the geometric data required for design. The program will now determine the thickness of each of the outer layers in the sandwich model as the lesser of the following. 1. Twice the cover measured to the center of the outer reinforcement, which is 3 inches, or 2. Twice the distance from the center of the slab to the center of the outer reinforcement, which is 9 inches. 3 inches is less than 9 inches, and thus the thickness of the outer layers will be 3 inches. The membrane stress resultants and moment stress resultants that impact the reinforcing in the one direction are M11, F11, M12, and F12. To convert the moment stress resultants into a membrane force couple, the moments need to be divided by the moment or lever arm. In this case, the lever arm is the distance between the top and bottom reinforcing in the one direction, shown as D1. Thus, for the M11 moment, the resulting force couple will be M11 divided by D1. However, converting the moment stress resultants into pure membrane forces is only half of the equation. Next, we need to convert the direct membrane stress resultants into pure membrane forces apportioned to each of the outer layers. We will distribute the pure membrane forces such that the moment equilibrium is maintained. That is, dt1 times ft1 equals db1 times fb1, where dt1 is the distance from the center of the shell to the top steel, and db1 is the distance from the center of the shell to the bottom steel. We know that dt1 plus db1 equals d1, and f11 equals ft1 plus fb1. Substituting these values into the first equation, we see that for the top layer, the resulting pure membrane force is f11 times db1 divided by d1. Thus, the total membrane force in the top layer due to M11 and F11 resultant stresses is N11 equals minus M11 plus F11 times dB1 divided by D1, as shown. A similar approach is taken with converting the M12 and F12 stress resultants into membrane force N12. The next step is to convert the pure membrane forces into design forces. There are a number of different conditions that need to be checked, but it may be as straightforward as N design equals F11 plus the absolute value of F12. Once the design forces have been computed for top and bottom and both directions, calculating the rebar intensities, that is, the required rebar area per unit width, is straightforward. In this case, the top reinforcing in the one direction is equal to the design force divided by phi times F sub y, where phi is always equal to 0.9. Now let's finish the model and go ahead with the design. We will select the entire slab, and in addition to the self-weight dead load, we will add a live load of 50 pounds per square foot, or 0.00035 kips per inch squared to our slab. We will also define a new load combination. Called slab design. And for our study, we'll define a single combination of 1.2 times dead plus 1.6 times live, although any number of appropriate design combinations could be specified. With the loads assigned, we will switch to a plan view, and we can now run the analysis. Next, we can move on to the design. However, the design is already done. It is automatically performed when running the analysis. No additional steps are required. To get to the design results, all we need to do is go to the Display, Show Forces, Shell command. Choose the Slab Design combo and select the Concrete Design option. Here we can select the face for the output, or maximums and minimums. And we will select the bottom face as it will be in tension and require the most reinforcing. Next is a list of components. Items such as the pure membrane forces, the design forces, and the area of required reinforcing are all available. First, let's view N11. And we get a value of approximately 0.59 at the outer corner for the outside bottom layer. Now we will switch to N12. And get a value of approximately 0.72 at the same location. Combining these two gives us a value of approximately 1.31. This is what we would expect the design force in the one direction to be. And if we select N Design 1, we find that it indeed does match the value. Next, we will display the area of steel required on a per unit width basis. For the bottom outside layer in the one direction, this is AST 1. This gives a value of approximately 0.024. This should be equal to the design force divided by phi and Fy. If we do the calculation, it does indeed match. Going to the display once more, the component F sub C represents the principal compressive force per unit width. And again, there are a number of different conditions that need to be checked. but it may be as straightforward as F sub C top equals minus 2 times F12. If we switch to the top face, since it should be in compression, and select the N12 component, we see that it has a value of approximately 0.72. If we select the F sub C component, we see that F sub C is indeed approximately twice the N12 value of 0.72. Lastly, S sub C is simply the principal compressive stress and is obtained by dividing F sub C by the thickness of the layer, which should give us a value for the top layer of approximately 0.48. And again, the value matches. In conclusion, it is a simple process to obtain required Eurocode reinforcement intensities for concrete shell objects using SAP2000. Note that these reinforcement values are based purely on strength requirements, and no serviceability or code minimums are checked. This concludes this tutorial on concrete shell reinforcement design in SAP2000.